Hello, welcome to the class. Today we are moving to the next section of the textbook. Currently we are in chapter 10, Theory of Graphs and Trees. The next section, which is 10.2, is matrix representations of graphs. Alright, so this is the first part of the section, and then in the next day I will discuss the other part of the section 10.2. Alright, in this section we're gonna learn how to represent graph in terms of a matrix, and then how to represent matrix in terms of a graph. Alright, first of all, let's understand what are matrices. Matrices are two-dimensional analogues of sequences. Alright, so you know about sequences. A sequence can be written down like this: a1 comma a2 comma a3 comma dot 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 an. So this is a sequence of n terms. This sequence is one dimensional. Okay, this is one dimensional. This is one dimensional. Now we going to discuss this the two-dimensional form of sequence technically. Okay, the two-dimensional form of this, which is called a matrix. All right, then matrices are also called two-dimensional arrays. Okay, two-dimensional arrays. So this is the definition of a matrix. And M by N matrix A over set S is a rectangular array of elements of S arranged into M rows and N columns. All right, so these elements are in S. These elements are in S. This is in S, that is in S, that is in S. All these elements are in S. Okay, these elements are in S. So you just rearrange these elements in an array of 2 by 2 array of two-dimensional. All right. So that is called a matrix, which has m rows, m rows and n columns. Okay, so these are the rows 1, 2, and it has m rows and then n columns, column 1, column 2, blah blah blah, column n. All right, so we call this is the ith row and this is the jth column. Okay, so this is the definition of a matrix. The short form of a matrix is this. This is the short form of a matrix. That's the short form of a matrix. Rather just writing this big thing, so you could write a matrix like this, which is in a simple format. All right. Then you're going to learn a little bit more about matrices. The ith row of A is the matrix here, as you see here. A is the matrix. All right. The ith row of A is given like this. This is the ith row. Okay, that's the ith row. So this is the jth column. Give me a second. It is hard to draw below. Give me a second. I will draw like this. All right, so that is the jth column. So you see that this is the ith row, which is marked in yellow, and the jth column is that which is marked in orange. All right, the entry aij in the ith row, the entry aij in the ith row and the jth column of A is called the ijth entry. Okay, these are just terms. These are just technical terms. An m by n matrix is said to have a size m by n. All right, if the matrix has m rows and n columns, we say the size of the matrix is n by m. Number of rows, and then this n is number of columns. If A and B are matrices, then A equals B if and only if A and B have same size and the corresponding entries of A and B are equal. There are two things. In order to say A equals B, you have to satisfy two things. The first thing is A and B have same size. Okay, the first condition to satisfy. And then the corresponding entries of A and B are all equal. Okay, so you have to satisfy these two conditions. Then you could write this thing, this equation. That means Aij equals Bij. That means each corresponding element is equal. As an example, let's say your matrix A is something like this. A11, A12, A1, A21, A22, and let's say your B matrix B equals 4, 3, 7, minus 1. If A equals B, you could say all the corresponding elements are equal. That means this equals that, this equals this equals that, and that equals this. All right, so that implies A11 equals 4, A12 equals 3, A21 equals 7, A22 equals 1 minus 1. All right, so if A equals B, and the other thing is you have to have the sizes of the matrices are same. Here the size is, we just write the size here. This size of this one is 2 by 2. Here the size is 2 by 2. All right, these are the sizes of the matrices. Go down. A matrix of which the number of rows and columns are equal called a square matrix. Okay, if it's a square matrix, number of rows should be equal to number of columns. All right, so you could write A like 4, 3, 2, 1. This is a square matrix. Okay, and then if you write B as 4, 3, 1, 2, 0, 4, this is not a square matrix. You can see it has 3 columns and 2 rows. Okay, so one is a square matrix, the other one is not. If A is a square matrix of size n by n, then the main diagonal of A consists of all entries A1, A11, A22, blah blah blah, ANN. That means this is called the main diagonal. Okay, that is called the main diagonal. Alright, it's marked in blue. That's the main diagonal. Alright, so let's go to the next slide. Then we have an example. In this example, we're going to learn a terminology of matrices. The following is a 3 by 3 matrix over the set of integers. Okay, so the set is integers. So these are the integers. All these are integers. Okay. Then part A of the problem, what is A23 in the what is A23, the entry in second row and third column. A23 means this is for the row number and that is for the column number. Okay, so you have to find what is the entry in the second row and third column. Okay, so that is A23 should be this element, which is 5. Then part B of the problem, what is the second column of A? Okay, then you have to find the second column. So you can consider this as the second column. That's the second column. So the second column here is 0, -1, 2. Okay, so I use square brackets to represent columns and rows. So since this is a column, I just represent it as a column here. I don't write this as that. This seems like a row of the matrix, so I will keep it like that. Alright, so part C, what are the entries in the main diagonal of A? Now you have to find the entries in the main diagonal. Those are the entries of the main diagonal. You can write them as 1, -1, 0. Okay, so I will just put curly brackets to represent them as a set. So this is the set that we are talking about, 1, -1, 0. Alright, then matrices and directed graphs. Now we're going to learn the relationship between matrices and directed graphs. Alright, so directed graphs are everywhere in science, especially in network science. Let's say if you consider an email network, that means if you consider Google, it is actually network. So there are people who are having Gmail accounts, and everybody is a node. If you have a Gmail account, you are a node in that big network, huge network. If you send an email to a person, then you can just mark an edge, a directed edge from you to that person. Let's say you send an email to Thompson today. So there's a directed edge between you and Thompson. The arrow is pointing from you to Thompson. And then you got a reply from Thompson. Then there's another edge from Thompson to you, having an arrow from Thompson to you. Like that, emails, Gmails actually can be represented as a big network. All right. So as I explained earlier, so you can consider airport network as a directed network. The airports are the vertices. If there's a flight going from airport A to airport B, then there should be directed edge. All right. So then you can see networks are everywhere in social networks, in sensor networks, and even in neural networks. If you consider your brain, messages are passed through neurons. Neurons are vertices. If a message passes from one neuron to the other neuron, so you can just mark that as a directed edge. All right, so there are a lot of practical applications in directed graphs as well as undirected graphs that we are going to learn very soon. But now let's see how to represent them as a matrix. Consider the directed graph shown in figure 10.2.1, which is this. This graph can be represented by the matrix A, for which Aij equals the number of arrows from Vi to Vj. For every I goes from 1 to 3 and j goes from 1 to 3. There are 3 vertices. All right, there are 3 vertices. These represent vertices: vertex 1, vertex 2, vertex 3. All right, so there's a directed. So these are the indexes. Indexes are actually the corresponding vertices. Now I'm going to put this into matrix. All right. First of all, what I would do, I need 3 vertices in this matrix. So I draw something like this. All right. So I mark this as V1, V2, V3, V1, V2, V3. All right. So I just mark the locations of this matrix like this. So this is the location V1, comma V1. This is V1, comma V2, V1, comma V3, V2, comma V1, V2, comma V2, like that. All right. There are 9 locations in this matrix. Okay. Now I'm going to read the graph. I'm starting from V1. There's an edge from V1 to V1, which is a directed edge. Since there's an edge from V1 to V1, I mark 1 here. Okay, so let me mark it different color. This is red. 1. There's one directed edge. All right. And thereafter, by the way, I will just take this out. Otherwise, this note will be messy. So this red is that. How do you mark it? I will mark by an arrow. So this red edge is this red entry. Okay, then from V1 to V2, that I'm supposed to put here. From V1 to V2, there's this. Okay, for that I use a different color. That thing. That is just one edge. Give me a second. I made a mistake actually. I made a mistake. Yeah, that's a good mistake because we can learn from that. I just marked 1 here, which is wrong. Why? This says there's an arrow from V1 to V2. There's an edge from V1 to V2, but that doesn't happen here, right? Edge is not that way. The edge is this way. The arrow goes reverse. So then I can't mark 1 here. Okay, so this says an edge from V1 to V2. No edge from V1 to V2. Actually, edge is from V2 to V1. Okay, so this is the arrow. So I will mark zero here. Okay, then V1 to V3. V1 to V3, no edge like that. Only edge goes that way. So this is also 0. Alright, so that's the first row. And then move to the next row. I use blue for the entire matrix, the rest of the matrix. V2 to V1. V2 to V1, there's an edge. Okay, which is that. So I mark 1 here. And then V2 to V2. V2 to V2, there's this loop. So it is 1 here. And then V2 to V3. V2 to V3. This is special. Why there are two edges? V2 to V3, there are two edges. So you put 2 here. Alright. And then from V3 to V1, there's one edge. And then V3 to V2. V3 to V2, none of the edges are there. And then from V3 to V3, no loops at V3, that's 0. So this is the corresponding matrix. We call this as the adjacency matrix. Okay, there's a new name for this. This is called the adjacency matrix. Adjacency matrix. Adjacency matrix explains the connectivity of the graph. All right, it explains the connectivity of the graph. All right, so just go to the next slide. Matrices and directed graphs. Give me a second. All right. Thus, actually this explains everything that I explained early. This explains everything I explained right here. Okay, this explains the problem, how it works. Let me read it because I have already explained that. Thus, A1 equals 1. Okay, that's this. Because there is one arrow from V1 to V2. Sorry, V1 to V1, which is the loop. Okay, which is the loop. Because there's no arrow from V1 to V2, then give me a second, I'm just confused a little bit. Let me repeat this. Alright, so first it says, thus A11 is 1 because there's one arrow from V1 to V1. That's great. A12 equals 0 because there's no arrow from V1 to V2. V1 to V2, there's no arrow. We explained that. A23 equals 0 because there are two arrows from V2 to V3 and so forth. Okay, A is called the adjacency matrix of the directed graph. For convenient reference, the arrows and columns of A are often labeled with vertices of the graph. That's what we have done already. Okay, we have done this. We just label those as vertices. Okay, so that's why I took this as V1, V2, V3, V1, V2, V3. So I label columns and rows as vertices. Alright, then definition. Let G be a directed graph with ordered vertices v1 comma v2 comma blah 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 vn. The adjacency matrix of G is n by n, is the n by n matrix that we write like this over the set of non-negative integers such that Aij equals the number of rows from Vi to Vj. All right, that's what we have learned early. So the entry represents how many arrows between those two vertices. This was 2 because there were 2 arrows from V2 to V3. Okay, there were 2 arrows. See, 1 arrow, 2 arrow. Okay, you understood that. Actually, it represents how many arrows in the directed graph. That is explained right here. Okay, I believe this is clear to everybody. This is the definition of representing adjacency matrix for a given directed graph. And then we have an example. Example 10.2.2. The adjacency matrix of a graph. The two directed graphs shown below differ only in the ordering of their vertices. Alright, the shape is same, you see. The shape of this one equal to shape of that. But the ordering of the vertices are entirely different. You see, this is V1, this is V3. This is V3, this is V2, this is V2, this is V1. Okay, the labeling is entirely different. Find the adjacency matrices. Now you have to find the adjacency matrices. You are given the graph, directed graph. Now you have to find the adjacency matrices. Okay, so you have the same example here. So I'm going to write the adjacency matrices. For that, first of all, I have to just understand how many vertices. There are 3 vertices, 1, 2, 3. Okay, so the matrix should be 3 by 3. This matrix A, which is 3 by 3. Okay, then I mark this as V1. And then V2, V3. And then this is V1, V2, V3. Alright, so now I have to fill this adjacency matrix. How many arrows from V1 to V1? No arrows from V1 to V1. That means no loops from V1 to V1. That means this should be 0. This is 0. Then how many arrows from V1 to V2? Here V1, here V2, no arrows, right? So this is also 0. Then how many arrows from V1 to V3? Here V1, here V3. How many arrows? No arrows from V1 to V3. There are 3 edges, but both of edges are going from V3 to V1, not the other way. Okay, so it is actually 0. So that is the first row, and then go to the second row. From V2 to V1, this place for V2 to V1, again no arrows, so that is 0. And then V2 to V2, there's one loop here. V2 to V2, there's one loop, so you could put one here. And then from V2 to V3, yes, V2 is here, V2 to V3, you have only one arrow. So this should be 1. All right. And then from V3 to V1, that is this location, V3 to V1, there are two arrows. So this should be 2. Then V3 to V2, there's one arrow. V3 to V3, no loops, 0. So that is the corresponding adjacency matrix. And then go to the next graph. Here also there are 3 vertices, so the matrix should be 3 by 3. V1, V2, V3. And this is V1, V2, V3. Alright, from V1 to V1, there's a loop. You put 1 here. From V1 to V2, V1 to V2, there's one edge, one arrow, it's 1. Then V1 to V3, no arrows, 0. Okay, then V2 to V1, there's one arrow. Then V2 to V2, no loops at V2. And V2 to V3, there are 2. And then from V3 to V1, no any arrow from V3 to V1, so this is 0. And V3 to V2, no arrows that way, so 0. And then V3 to V3, no loops, 0. So these are the corresponding adjacency matrices. All right. So these are the corresponding adjacency matrices. Now you can see these graphs look like. These graphs look like, right? These graphs look like, but adjacency matrices are entirely different. And I'm sorry, I wrote it wrong. Adjacency matrices are totally different. Actually, I have to get these things below. Let me pull these things below. Okay, they should be right here. All right, good. And then let me get this below too. All right, good. So that is the solution for example number 10.2.2. And then just move to the next example, which is 10.2.3. This is a 4x4 matrix. That means this the graph representing this matrix should have 4 vertices. So let me mark those 4 vertices. Let me take this as V1, V2, V3, V4, V1. Let me mark them on the other side. V1, V2, v3, v4, right? So these are the vertices. So now I'm gonna transform this into a graph. All right, so let me draw that. So I have v1 here. First I will just mark these vertices like this. Later I will just change these locations if they are messy. Okay, so let me take this as v1, v2, v3, v4, and then I'm going to mark them. From v1 to v1 no loops, then v1 to I'm a little confused. Let me get them to the other side. Otherwise this is fine though, but it is very easy to read if they are in the other side. All right. And then this is for v1 to v2. There's one arrow from v1 to v2. There's a directed edge, v1 to v2. Okay, and then here this is one from v1 to v3. There's a directed edge, and then no directed edge from v1 to v4. And then v2 to v1, there's a directed edge, and then v2 to v2, that means there's a loop in v2, and then no directed edge from v2 to v3, and there are two directed edges from v2 to v4. There are two directed edges from v2 to v4. Alright, from v3 to v1, no edge. From v3 to v2, no edge. From v3 to v3, there's one edge. That means there's a loop at v3. And then from v3 to v4, there's another arrow. And then go to the fourth vertex, v4 to v1, there are two edges. v4 to v1, there are two edges. And then v4 to v2, there's an edge. It's a little messy. And then let me mark this somewhere. I will mark this as the loop. And then no directed edge from v4 to v3, no directed edge from v4 to v4. So this is the corresponding graph represented by that matrix. All right. So this is explained here. There are some, I used few slides to explain this. In the first slide it says, let G be a graph corresponding to A, and let v1, v2, blah blah blah, v4 be the vertices of G. I explained this already. I just put this on the note because you can read that later. So you have everything written down right here. Label A across top and down in the left side. You have to label A across top and down, from top to down, in the left side. So this is the left side, that's the right side. So you mark like that. Then thereafter, you have to understand what are the directed edges. For instance, the two in the fourth row and the first column, that two means there are two arrows from v4 to v1, okay, that we have already done here. So this explanation is giving you all the necessary information. Okay, and then the 0 in the first row and the fourth column represents there is no arrow from V1 to V4. Okay, that's because of the 0. A corresponding directed graph is shown here. So here is the place where I have to draw the directed graph. Now I'm going to copy that graph here. Okay, let me then get that graph. Alright, so graph is right here. Okay. Alright, so that's end of example number 10.2.3. Now we move to undirected graphs. Since we learned directed graph, learning undirected graph is easy. The difference between directed graph and undirected graph is in directed graph there are arrows. In undirected graphs you don't have arrows. They are just like this. Okay, the direction is not specified. It is something like the Facebook network. Alright, it is not like the email network. In the email network there should be an arrow that represents emailing from one person to the other person, but in Facebook network it is just the connection, whether you are a friend with somebody or not. Maybe the LinkedIn network or the Twitter network. Alright, so those are undirected networks. We are going to learn about these with more details when we do project number 1, the first project. Okay, once you know how to associate matrices with directed graphs, the definition of matrix corresponding to an undirected graph should seem natural to you. So it's very straightforward. As before, you must order the vertices of the graph, but in this case you simply set the ijth entry of the adjacency matrix equal to the number of edges connecting to I and jth vertices. Okay, now you don't care whether I connected to j or j connected to I. Here you simply check whether they are connected or not. If they are connected, then that's number. Let's say there are two vertices, v and u. They are connected by two edges. So in the matrix, in the adjacency matrix, this location represented by 2. Okay, so that's very straightforward. Here you have the definition which explains what I explained right now. Let G be an undirected graph with ordered vertices v1, v2, blah 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 v1. The adjacency matrix of G is the n by n matrix that over the set of non-negative integers such that Aij equals number of edges connecting Vi and Vj. Okay, so this simply number of edges connecting these two vertices. Let's say you are given this graph. Let's say this is a huge graph, but I am representing a part of that. Let's say this is Vi and that is Vj. Okay, there are two edges. All right, now AI in this matrix, this is ith row and this is the jth column, and this element is actually a I j, which equals two. Alright, you can understand that because there are two edges between I and j. Alright. Alright, so that is explaining this definition. Example 10.2.4. Finding the adjacency matrix of G. Find the adjacency matrix for the graph G shown below. Okay, so you are given the graph, now you have to get the adjacency matrix. Alright, so I'm going to make the adjacency, I can make the adjacency matrix right here. So this is the last example in this part of the section. Here it has 4 vertices. 1, 2, 3, 4. There are 4 vertices. So the matrix should be 4 by 4. V1, V1, V2, V3, V4. Let me mark them again. Okay, this is V1, V2, V3, V4. This is the location for V1 and V1. That means no loops, so this place should be 0. This is V1 between V1 and V2. V1 and V2, there's one edge. This is 1. And then this is V1 and V3. No edges between V1 and V3. So this is 0. And this is V1 and V4. V1 and V4, there's an edge. So this should be 1. Let me check this one. This is V1, V3. Yes. Give me a second. I will check whether I made a mistake here. Alright, so this is 0. And then go to the next vertex, which is V2. V2 is right here. And from V2 to V1, yes, 1 here. And V2 to V2, yes, there's a loop. And V2 to V3, there are 2 edges. And then V2 to V4, there's one edge. Alright, so that is about the second vertex. And then go to the third vertex. From V3 to V1, no. From V3 to V2, yes, 2. And V3 to V4, no. Sorry, V3 to V3, no loops in V3. So V3 to V3 is 0 and V3 to V4 is 0. Alright, so now we are moving to the next vertex, which is V4. From V4 to V1, yes, there's 1. V4 to V2, there's 1. V4 to V3, no. And V4 to V4, yes, there's 1. Okay, this is the corresponding adjacency matrix. All right, this is the corresponding adjacency matrix. Once you have the adjacency matrix for an undirected graph, you can see something very interesting. What you see here is that is symmetric. Check whether you can recognize that. This matrix is symmetric. Okay, this symmetric is symmetric. Symmetric means you make the main diagonal, that is the main diagonal. So the right triangle is same as the left triangle. This is the main, let me mark this. This is main diagonal. Let me use a different color. Sorry. This is main diagonal. Okay, now you can see it is symmetric. See, this is the upper triangle and this is the lower triangle. Okay, they are symmetric. Alright, so upper triangle and lower triangle are symmetric. They are same actually. You can just take this triangle and then put this triangle upon that. Okay, you can take the above triangle and then just lay on that. They are same. Alright, so you know the symmetry now. This is a nice property in undirected graphs. Okay, so that is the end of today's class. In the next day, I will start the second part of this section. Thank you very much.